All right, you are welcome to this session, and in this video I'm going to be giving you expert analysis on what you are required to know or what you are required to do in the WAEC Physics Practical question number one. Question number one, like I said, I'll be giving you expert analysis, and with this you'll be able to predict exactly what you are going to see on the day of exams. But before we go into the experiment proper, I would like to give you a little theoretical background. Mind you, this video may be a bit lengthy, but if you can stay tuned, you are going to learn a whole lot from there. So stay with me. So you are provided with the following things. You are provided with two identical spiral springs. I'm going to be showing you that in a moment. Two retort stands with clamps, a meter rule, a stopwatch, and a set of standard masses, a thread, and adhesive. That is something you use to gum or hold two things together. So if you are provided with these things, let us look at the theory behind the practical that you're supposed to do with this. Okay, if you can recall from simple harmonic motion that the period of oscillation of a loaded spring is given as T is equal to 2 pi into the square root of m all over k. This m is actually the effective mass of the entire system that is oscillating. But in this experiment, there are two springs provided. So when you are provided with two springs and these two springs are used in parallel, then you should know that the effective spring constant will be k plus k if each of them has a spring constant of k. So the effective spring constant will be 2k, because when you add k to k you get 2k. It will be 2k. And if you have 2k, it means what we are supposed to have here is 2k, since there are two springs that are used in parallel. So we continue. Now remember that in this equation, T represents the period, M here represents the effective mass of the entire system, while we have 2k here for the spring constant. So what we should have is that because when the system is oscillating, it is not just the standard masses that will oscillate, but the meter rule and even the spring as well. So this M effective, or this effective mass of the system, is actually equal to the load which you are adding to the suspended rule plus the mass of the meter rule plus the mass of the spring, which will be 1 over 3m, or if you like, mass of spring all over 3. So that's what the effective mass here is going to be. So this equation can be rewritten as T equals 2 pi into square root of the standard mass plus the mass of the meter rule plus the mass of the spring all over 3 divided by 2k. So you can rewrite this expression like this. If you take the square of both sides, you should have something like this. T squared is equal to 4 pi squared into m, let's say all over 2k here, plus the same thing, 4 pi squared all over 2k into mr plus mass of the spring all over 3. Now the reason I have separated this is that in this experiment you are going to be varying the mass, the standard mass. That is why I have separated this. So if you look at this, it looks like a standard straight line equation in the form of y equals mx plus c. So that if you plot a graph of t squared on the vertical axis against m on the horizontal axis, you are going to have a slope that is equal to 4 pi squared all over 2k. If you like, you can simplify further to give 2 pi squared all over k, and that will give you the slope of the graph. Again, you also have an intercept. The graph will have an intercept, and that intercept is going to be equal to 4 pi squared all over 2k into the mass of the rule, the mass of the meter rule, plus the plus 1/3 of the mass of the spring used, plus 1/3 of the mass of the spring used. And there are two things we can get from this slope and the intercept. One, we can get the spring constant of the springs used from the slope of the graph. And your graph is going to look something like this. You should have a graph like this where you have t squared on this axis, you have t squared on this axis, you have m on this axis, m in grams, while t squared is in seconds squared, and then you have a line like this. You have a line like this. If this line is extrapolated, it should cross the horizontal axis somewhere here. And this point where this graph crosses the horizontal axis gives the mass of the meter rule used and the springs also used in this experiment. So if you actually want better explanation on this, you can let me know in the comments so that I explain that further. But for now, this is the basic theory behind this experiment. This is the theory behind it. So I'm going to move on to show you how the experiment should be conducted. And I'll have clear procedures that will guide you on how to conduct this experiment. So here you have the setup, the diagram for the experiment. This is a rotor stand, this is another rotor stand. These are two spiral springs. This is the meter rule suspended horizontally from the two spiral springs, and these are your standard masses placed at the midpoint. So you are required to set up the experiment as shown in the diagram above, with the meter rule suspended horizontally using loops of thread attached to the two identical vertical springs. To continue, you ensure that the springs are clamped securely to the rotor stands, and the horizontal distance between them along the meter rule is 90 cm. So along the meter, that is the space between the two springs should be 90 cm. Again, you place a standard mass m equal to 150 grams at the center mark of the horizontal rule, firmly with the adhesive provided. Sometimes you may use a masking tape, a cello tape, or plasticine. Now, you displace the loaded meter rule vertically downwards by a small distance and release it. So the entire system performs vertical oscillations. Then you measure and record the time t for 20 complete oscillations twice and determine the mean time t, which is equal to t1 plus t2 all over 2. Now you obtain the period of oscillation by dividing t here all over 20, since you are taking 20 oscillations. Okay, then you also evaluate t squared, that is the square of the period. Now you repeat the entire procedures for other values of m equal to 200, 250, 300, and 350 grams. And in each case, you obtain the values of t, that's small letter t, the period, and the square of the period. You tabulate your readings or your results. and you'll be required to plot a graph of t squared on the vertical axis against m on the horizontal axis, starting both axes from the origin. Then you determine the slope s of your graph and the intercept p on the horizontal axis. Like I explained earlier, those two things would be useful in determining some things. So because I do not want the video to be too long, I'm not going to go beyond this. I will not write further on the things that you should be asked to determine. But if you need them, you can get them on the comment. Then take note that these are not, or this is not the only graph you can plot from this experiment. So in case it turns out you don't see something exactly like this, you may also be asked to plot a graph of t on the vertical axis against square root of m on the horizontal axis. Another way it could come is you may be asked to plot a graph of log t on the vertical axis against log m on the horizontal axis. In each case, you are going to have a straight line graph with an intercept on the vertical axis and a negative intercept on the horizontal axis. So I'm just going to take you through what the experiment should be so that you see the step-by-step procedures on performing the experiment. Alright, since I am not performing this experiment in the laboratory, there are a few things that may not be available. So this is your meter rule. This meter rule will be suspended horizontally from these loops of thread. You have a loop here, and you have another loop here. There are two loops of thread. So I'm going to suspend the rule horizontally. So you can see what I've done here. This is the meter rule suspended horizontally from the two springs. And then I'm going to add a standard mass. I'll place it at the midpoint. Here I'm using a masking tape to hold this standard mass firmly to the meter rule. So I'm using the masking tape. So I take up the stopwatch here and I'm going to displace this system such that it performs vertical oscillations, and you see what this looks like. So this is it. I hold this and displace it or push it down a bit and release it and count. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So after timing it once, you take it again. You may either pull it down or you raise it up. So I'm going to pull it down a bit, and then again I time it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I have around 12 seconds for this mass. So you would repeat this procedure, using the other masses like 200, 250, 300, and 350. And afterwards, you are going to prepare a table. So I'm going to show you what your table should look like right now. So this is what your table should look like. You have serial number here, you have mass in grams, you have T1 in seconds, you have T2 in seconds, you have T, which is equal to T1 plus T2 all over 2 in seconds. You have the period capital T in seconds and T squared as well. Take note of all the rules involved in preparing a good table of value. You must maintain the same number of decimal places in each case. Because we do not have enough time, that is why I'm not going to list you the values that I obtained in my own experiment. But if you are interested in that, you can contact me through the number displayed on your screen. So that is it. That is what you are supposed to know. Remember that you would be asked to state precautions. You will also be asked some other questions involving simple harmonic motion, Hooke's law, and the likes. And also, you may be required to use your slope to calculate the value of the spring constant. And it is very, very simple. The slope of your graph, slope, is actually equal to 4 pi squared all over 2k. 4 pi squared all over 2k. So once you make k the subject of the formula, you will get the spring constant. And as well, you may also be required to find the intercept of that graph on the horizontal axis. It's going to give you a negative value. That intercept gives you, on the horizontal axis, gives you these values. So you should be able to know the mass of the meter rule that is used. They may not ask you for this, but they probably ask the teacher in charge to state the mass of the meter rule used. And if that is requested, then it means you must do this correctly so that you state your intercept shows these values. So that is it for question number 1. That is it for question number 1. I will be dropping other videos that feature expert analysis of question number 2 and expert analysis of question number 3. So like, share, and comment so that other people will see this video. And don't forget to contact me if you need further clarifications on any of these things. Thank you very much. See you in the next video.